Welcome to AI Frontiers. Today's episode, AI that understands the next leap in language, presents insights from 64 groundbreaking computational linguistics papers released in December 2025. This exploration covers advances in machine understanding, reasoning, fairness, and inclusivity. Join us as we examine how the latest research is propelling artificial intelligence toward robust, transparent, and truly human-centered systems. In this deep dive, we will unpack 6 major research themes shaping the present and future of computational linguistics. Key breakthroughs in model safety, advanced reasoning, and data efficiency will be discussed, alongside 3 seminal papers that are transforming the landscape. The session concludes with actionable insights on how AI is becoming more fair and accessible, equipping you for the next era of language technology. Computational linguistics stands at the intersection of computer science and the intricate realities of human language. This field powers chatbots, translation tools, search engines, and more, striving to enable machines to genuinely understand and generate natural language. Its influence extends to global communication and cultural exchange, with current research focusing on empowering technology for everyone, regardless of background or language. Theme 1 centers on large language models and multimodality, marking a new era for AI capabilities. Contemporary models are now able to process not only text but also images, audio, and code, often in combination. The work by Wu and colleagues demonstrates that parallel reasoning can significantly boost both performance and speed, while Young and collaborators highlight the unique safety challenges posed by multimodal systems. This evolution enables more sophisticated applications, ranging from programming aids to vision language tasks. The technical concept of multimodality refers to AI's ability to understand and integrate multiple data types within a single model. The second key theme addresses robustness, alignment, and safety, critical factors in making models trustworthy. Young and colleagues found that even trillion-parameter models remain vulnerable to adversarial attacks. Incorporating a deliberative reasoning step, where the AI pauses to reflect before answering, was shown to reduce unsafe outputs significantly. Radhashankara and team highlighted that models can be influenced by user bias, underscoring the importance of inference time defenses rather than simply increasing model size. The technical concept of deliberative reasoning emphasizes the value of AI systems that self-monitor and reconsider their responses prior to output. The third theme focuses on fairness, explainability, and human-AI collaboration, which are essential for building systems that are both trustworthy and inclusive. Radhashankara and colleagues advocate for actively seeking contradiction, not just confirmation, as a means of improving model reliability. Explainable AI techniques now provide transparent decision-making in multimodal systems, ensuring that similar cases receive similar treatment. Human-AI teamwork is emphasized, with AI systems designed to fill knowledge gaps and reason interactively with users. Newly developed benchmarks test these models' understanding in realistic, real-world contexts. Theme 4 highlights low-resource languages and data efficiency, advancing the democratization of language technology. Researchers have shown that compact models can be successfully adapted to underserved languages using smart fine-tuning strategies, achieving significant impact without requiring massive resources. This inclusivity ensures that technology reaches speakers worldwide. Radhashankara and team demonstrate that efficient retrieval processes can reduce hallucinations, further improving reliability. The technical concept of retrieval-augmented generation refers to AI systems grounding their answers in verifiable external evidence, rather than relying solely on internal knowledge. In Theme 5, the focus is on evaluation, reasoning, and temporal understanding, all of which are essential for raising the bar of real-world AI. New benchmarks are being developed to test semantic nuance and cross-cultural understanding. Wu and colleagues show that parallel reasoning outperforms traditional step-by-step approaches. Hybrid systems which blend neural networks with symbolic logic are enhancing temporal reasoning capabilities. Ongoing research explores how explainability can be aligned with a model's internal reasoning processes. Evaluation using human-annotated data provides accountability and ensures that models perform reliably in practical scenarios. The key findings from 2025 reveal several transformative shifts in computational linguistics. Parallel reasoning, as demonstrated by Wu and collaborators, breaks the sequential paradigm, allowing models to solve problems more efficiently. Model size alone does not equate to safety. Even trillion-parameter systems remain susceptible to adversarial manipulation, as shown by Young and team. Active contradiction seeking, highlighted by Ravishankara and colleagues, substantially reduces model hallucination. Small models are now capable of supporting low-resource languages, and explainability techniques have expanded to cover multimodal real-world tasks. Researchers achieve these advances through a diverse set of methodologies. Reinforcement learning enables models to learn optimal behaviors through trial, error, and reward signals, excelling at complex reasoning and tool use. Retrieval augmented generation grounds AI outputs in external documents, enhancing factual accuracy. Neurosymbolic systems combine the pattern recognition of neural networks with the structured logic of symbolic reasoning, facilitating advanced capabilities like temporal tracking. Modular augmentation allows for specialized plug-and-play modules to be added to existing models, while human annotated benchmarks ensure realistic, high-quality evaluation. The first seminal paper spotlighted is Replicating Tempest at Scale by Young and colleagues, which tested 10 large models using adaptive, multi-turn adversarial attacks. Results showed that model size did not predict safety, with most models breached easily. However, introducing deliberative reasoning cut the attack success rate in half, demonstrating that robustness requires new inference strategies, not just more data. This work is notable for its scale, experimental rigor, and its urgent implications for AI safety. The next influential paper is Falsification Verification Alignment by Ravishankara and team, focusing on mitigating sycophantic hallucinations in AI. They introduced FVA-RAG, a method where AI actively seeks out contradictory evidence to challenge its own responses. This approach dramatically reduced hallucinations and sycophancy in retrieval tasks, all without the need for retraining, as it operates at inference time. Such methods are essential for high-stakes domains like medicine, law, and fact-checking, and this paper was selected for its novel and practical impact on building trustworthy AI. The third seminal work, Native Parallel Reasoner by Wu and collaborators, presents a teacher-free framework that trains models to reason in parallel, breaking away from traditional sequential processing. This approach produced up to 24% performance gains and a 4-fold increase in inference speed, all without external supervision. The native parallel reasoner overcomes the sequential barrier in language model design and was chosen for its significant impact on efficiency and model architecture in artificial intelligence. Looking ahead, several promising directions are emerging in language AI. Priority areas include developing models capable of reasoning, explaining, and verifying their outputs in human-like ways, especially in high-stakes tasks. Robust adaptive defenses against adversarial attacks are increasingly critical. The expansion of AI technologies to support a wider array of languages, modalities, and domains is ongoing, with a strong emphasis on efficiency and fairness. Real-world evaluation methods are being refined to better reflect global user needs, and hybrid systems that integrate neural, symbolic, and human-in-the-loop components are expected to drive further innovation. This synthesis was constructed using GPT 4.1 by OpenAI, with text-to-speech provided by Deepgram and visuals generated via Grok image creation tools. A human expert reviewed the final synthesis to ensure technical accuracy, though minor oversights may persist. All references for the research discussed are available. AI Frontiers remains committed to transparency and continuous improvement in the dissemination of cutting-edge AI research. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from arXiv. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses arXiv.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by arXiv.org.